Cool. I'll start. Yeah, thank you for inviting me. Like you said, yeah, my name is Thomas George Thuruthel. Just recently joined as a lecturer at UCL, although working part-time at University of Cambridge at the moment. And for today's talk, I'll be talking about essentially how do you develop controllers for soft robots, and specifically minimalistic controllers. Hopefully by the end of the talk, you'll understand what I mean by minimalistic controls. And this is most of this work that I'm showing here is from my PhD in Scholarship Santana and some of my recent work at the University of Cambridge as a postdoc. Right, so getting started. So whenever I go to whenever I go to soft robotic conference, I typically get the notion that people believe that there's a trade-off between natural dynamics, or if I may call that morphological computation, and controller complexity. So people think that if your controller is too complex, then you're kind of offsetting or your natural dynamics, and vice versa. If you have a nice body, then you don't need a complex controller. But I think that is not the right way to look at it. In my presentation, I think what I am proposing is there's like a trade-off between natural dynamics and feedback control specifically. So feedback controller is the villain, which kind of offsets your natural dynamics. And I think it's not a new concept. I think maybe a lot of people might be familiar with this. There is a good work by Cosimo della Santina, who talks about this on a more theoretical side. I'll be giving some empirical evidence for that through some of our works. Yes, starting with our typical illustration of an embodied agent coming from Fumiya and Rolf's work in science. This is more an extended view of that. So what is an embodied agent, and what are the four key elements involved in that? So there is the brain, the controller, the body, and the sensor, which together constitutes the agent, which is interacting with the environment. So there are a lot of loops in this where information and energy flows through, and some of them are more important over the others. And I'll try to explain some of these controls using these loops, hopefully. Starting with what would be an ideal control. So in my point of view, I think an ideal controller would essentially be without any control. Right? If your body can do everything that it needs to do when it's interacting with the environment without the involvement of the brain, that would be the perfect controller. So there was a nice simple work that we did when I was in my PhD, which shows this example. So here we made this bistable gripper, soft gripper, which essentially can close on contact. So there is this purely mechanical feedback loop, which allows it to grasp objects without any sensor or controller. And it works with using bistable mechanism. So this gripper has only two stable equilibriums. One is an open and closed state, and you can offset the energy levels of these two states by playing around with the mechanics. In this case, you have a silly gripper with a ring around it, which gives these two binary stable states. I think the video will be more illustrative of how it works. Yeah, so that's more or less how it works. You have like a soft gripper with this ring, which gives it two stable states, and you can transition from one state to another by applying energy at the center. And the closed state is more stable than the open state. You can tune the stability region so that you need very little energy to transition, and then you can create like a simple closed loop grasping system. And I think towards the next video, we'll show you how you can use it for closed loop grasping. One of the cool things that you can get with these kind of simple designs is that you'll clearly get the fastest possible response because there's no multiple translation of information. So mechanical information directly gets transformed to another mechanical action. You can really get the fastest closed loop system per se. And that is very interesting. But then on the other hand, it's not very adaptable. So you can only do one task. You cannot program it. It's not very useful for practical application, but it's a nice concept to kind of illustrate what you can do with purely the body. And to understand what kind of controls you don't need, I can also describe one of the first works that I did during my PhD, which is on developing static controllers, or you can also call them kinematic controls. And they're not very good because they have this very high bandwidth low level control, which has very high bandwidth, which makes your system essentially very rigid, even if it's a soft bodied system. And this is more or less what Cosimo talks about in his paper that I was referring to before. I'll quickly go through what that means and how we develop a kinematic controller. It's still commonly used, although, like I said, it's not an optimal way of controlling soft robots. So in soft robots, I think kinematics and statics can be like analogous, and that's the only way of defining the kinematics, because you have virtually infinite degrees of freedom. The only way your kinematics can be fully defined is if you work only in the static regime, which means that if I give a constant force and a constant pressure or constant tendon length to my soft robot, it'll eventually settle at a fixed point. And this relationship can be mapped, and that can be a forward kinematics. And the control problem is finally inverse. So if I want my robot to go to this position, what kind of static force should I give? If you're familiar with the inverse kinematics, we have the same issues that you cannot directly learn the inverse kinematics because of redundancy. So you need to find a way around it. And so we use something called learning the differential inverse kinematics, which means that you're not learning the direct inverse kinematics, but you're learning local inverse kinematics. And to explain it more easily, what I would say is that the controller figures out how do I move my actuators locally so that I reach my target, so that I go closer to my target. It doesn't reach it, but it goes closer. And if you do that in a loop, it'll eventually reach it. And that local problem is learnable. So you learn that, and then you iterate over it over time. And then you can develop simple controllers. I would call them simple, but they do their task, but you can see they're not very accurate. Their motions are not very smooth from what you would expect from a soft robot. But because of the feedback loop, they can at least still have adaptability, so they can go around obstacles even if they don't know where the object is. So there is that adaptability, so it can interact with the environment, which you cannot really do with if you have just a purely mechanical system. So there is definitely advantage of feedback, but then, like I said, these kind of controls are not optimized. So you're spending a lot of energy because you're always stopping. You're always going to static conditions. That's only when your forward model is valid. So they're not ideal. And to make the point clearer, I think what I would say is, if you look at all possible state space that a soft robot can occupy, how we develop kinematic controllers is by essentially constraining our controller to always stay at this static regime. So essentially, you're making your robot, you're making the problem simpler by making the robot just follow a very narrow regime in its state space. Clearly, that is not optimal. You're not using all the capabilities of your soft robot. And you can solve that by using like essentially a dynamic control. And more specifically, I think open loop controllers are ideal if you want to fully exploit the natural dynamics. And notice that there's no feedback loop in this case. And I think I'll go a bit more in depth in how you develop these kind of controllers, because they're quite interesting. Not many people work on this. Recapping dynamics. So for any kind of robot, any kind of general robot, this is how you would formulate your dynamics. So given the inputs, which is you observe how your states transition over time. You cannot observe the full state. You assume that you cannot observe it, so your observations are only output y. And for a soft robot, the state, which is x, is not easy to understand. For steady state, we know exactly whether that can be done, but for the fully dynamic case, we cannot really formulate what is x. It's essentially a very high dimensional variable. The outputs are observable, like I said, but it is not fully descriptive of what is happening to the state. So it's a partially observable system. Like I said, there's a large degrees of freedom, and it's partially observable. So formulating the dynamics or even learning the dynamics is not very straightforward. There's a way around it, which we worked on during my PhD, which is on not learning the forward dynamics per se, but learning something called the forward output dynamics, which means that whatever variable, independent variable you're observing, you're trying to formulate a dynamical system or an equations that would describe how these output variables evolve over time. This is not straightforward, so it's not at all easy to derive this set of equations analytically because it's a partially observable system. But it is theoretically possible, and I'll attempt to kind of give you the idea about how this is possible. There is an assumption that you know exactly how the initial conditions of the system is. So either you know it or you can control it. So saying that at t equal to 0, I know exactly what all the states of my robot is at. From there, I can keep tracking what happens to my output, and then always have a formulation of how the output states will vary. And how you do that is by doing this iterative loop. So given my initial conditions and my initial input to the system, I can of course predict what will happen to my outputs if I can have a mathematical model of that. And then from there, I can iteratively give that output and the next inputs to iteratively predict what goes on in the future. And this is possible by keeping track of whatever has happened in the past. And the amount of time you should look in the past depends on how much you're observing. So for example, if y is exactly the same as your state x, then you don't need to look into the past. You just need to observe what happened in the last time step. But if you're like not observing everything which is happening to the state, then you need to look at some time horizon in the past. So we cannot really say how far behind we should look. We can always say that there is some finite interval to which you should look at, and then if you can do that, you can always formulate a function which can predict what happens to your outputs. This is a bit tricky to understand. If you don't understand, that's not very important. But essentially, what you're trying to do is learning this forward output dynamics model. And if I can do this, if I can learn this model, then I can use any kind of optimization tool to find out what should be my control inputs over time so that I can control this output variable. If we don't really care about the actual states of the robot, we can still control the output variable. So it could be like your end effector position. I can develop a dynamic model which describes how the end effector position will evolve over time, and then I can control it over time also. And in order to learn it, we use something called recurrent neural networks. If you're not familiar with it, think of a simple feed-forward neural network shown here. That plus some recurrent connections, which means that there is an external. So these networks also get back whatever it has predicted in the past as one of the inputs to these networks itself. Think of it, yeah. So essentially, they are dynamic neural networks, not static ones. Another way of visualizing it, which I find useful, is like it's like if you can unroll an RNN, these are like multiple feed-forward networks which kind of have changing inputs or changing memory every time you call them. So even if your input is constant to the network, the output always changes over time. So going back to our formulation, so we said that it's possible to learn this output dynamics, and we're hoping that if we give enough data to a recurrent neural network, it will, by the data, hopefully be able to store in its memory what has happened in the past, and then develop this model that can predict what happens to the output. And like I said, it's very difficult to do it analytically. For learning, it's very easy. So that's more or less what's shown here. I also described a little more in detail how we do it. So like I said, we can use an RNN to develop this output forward dynamics. You set up your software word, observe the output. So in this case, we are looking at the end effector position only. Do some random motions. Are you able to hear the video? Or sorry, audio? I can't seem to mute it, but you do some random motions. Observe this. what happens to the output for the given input, and then use your RNN to learn this mapping. Once you do that, like I said, you can do any simple optimization techniques, which tries to find out what is the control input that takes you to my desired output. So if I want to reach this position, I can do an optimization to find out what control inputs take me there. So you can formulate that like an minimization problem, put constraints. One of the constraints is actually the forward dynamics itself. And then you can put limits on the amount of force you can apply. And then you can find out like, in this case, you can find open loop trajectories which take you there. Give you some examples of how you do it. This is an example in simulation. So the model itself is an analytical model, and we're using RNN to essentially learn the model. So one of the clear advantages you can see is that the model, which is mathematically formatted, is very computationally expensive, but this learned model, even though it's doing the same thing, it's very cheap. It's very fast to solve. So essentially, it's all in this really complex ODE in a closed form. We don't really know how it does it, but it does it much faster than what we can do it. And it's also very quick to learn. So you don't need a lot of data to learn. So in this case, it was just like 70 seconds of real-time data. And then you can get a fully forward dynamics model using RNN. And then, like I said, do an optimization. So in this case, it's like a soft octopus continuum robot. And I want to reach this position, which is shown in green. And then you can find out the control input, which takes me there. You can do the same thing for a real system shown here. Again, it's really fast to learn the dynamics. There are multiple reasons for this. I might come back to this later. But for this case, it just needs 4 minutes of data. So you use this motor bubbling for 4 minutes. You collect some data, give that to this RNN, and it's very stable. It learns very well. And then you can find out, you not just control your robot position, but you can also control it in time. So you can go in circular motion in slow way, and I can do that in a fast way. Also do some traditional ball in the cup task. Might not play the video because the audio is kind of jarring. I think what is most interesting that came out of this work was how a lot of these open loop trajectories. So there's no feedback. The controller is run in open loop, can exhibit really nice stable behaviors. So this is one of the works that we showed where there are a lot of these stable open loop trajectories, which are highly robust. Let me see if the video plays. It's a bit slow. So to recap, so we learned this forward model, and then using this learned model, we can observe what the trajectory of the robot will be if I give some closed loop inputs. And you can see that a lot of these open loop trajectories are self-stabilized, which means that if I disturb them without any kind of external feedback, they'll come back to this trajectory very precisely, like sub-millimeter precision, without any kind of feedback, and also reliably. So it's a globally stable limit cycle. And you can also find out multiple open loop trajectories. So you can find like figure 8s, star-like trajectories, which are very stable, globally stable, highly robust, and also highly repeatable. So you can do like pick and place tasks without knowing anything about the environment, but they will be, even with interactions, they'll always follow the same trajectory. So that's something that you really associate with soft robots, but they can be highly repeatable if you want them to. And all this comes because of this open loop control strategy, I believe. Again, these are limited because if you really want to interact with the environment and change the state of the environment, which is, let's say, in manipulation tasks, in that case, you have to rely on feedback. You need some sort of feedback on what is at least happening to the objects in the environment. So you cannot really, for practical reasons, always rely on open loop or purely mechanical feedback. So you need to have feedback, but you don't really want it to be high bandwidth. You don't want to restrict. You don't want to make the controller very stiff. And yeah, like I said, this is very important when you're working with manipulation. So one of the areas that I'm researching on and heavily interested is in tactile manipulation using soft robots. And in this case, you need definitely like some sort of feedback. ideally tactile feedback. So some of the recent works that I've been working on in University of Cambridge is looking at that. I'm also trying to incorporate all this kind of open loop control strategy. So here we have this really nice anthropomorphic hand. So with rigid skeletons and some soft joints with a nice skin, which has a few amount of sensors on it. So in this case, it's like more or less like 16 sensors that are useful. They're not similar to the human skin in terms of tactile sensing, but in mechanical aspects, they're very closely related, similar to what we have. So the hand itself is completely passive, but it's mounted on a UFI arm, which is essentially doing all the control. And this, even with this passive hand, and you can do a lot of manipulation tasks. So one of the advantages of having a passive hand, which is mounted on this very precisely controllable rigid robot, is you can do something like kinesthetic teaching. So here we see Kiran, who's the PhD student working on this, teaching the robot how to pick up an object through demonstration. So he shows the robot how to do it once. The hand itself is passive, so you can just record what happens to the encoders in the rigid robot, teach it once how to pick it up, and then once this trajectory is saved, the robot can essentially repeat these things multiple times. So it's very easy to kind of teach it how to use the manipulations, and it's easy to teach it because one is because of the anthropomorphic nature, and also because of some of this passive interaction that we can do with the soft hand. And in this experiment, we are also varying how it picks it up every time. So we are adding some noise in the environment and also observing what happens to the sensors. So using all this information, like I said, you get this trajectory, look at how the sensor states change over time. And because it's all open loop, again, there's no feedback in the system. Once it is recorded, the arm carries out the same motion again and again. Because it's open loop, looking at the sensor data, we can actually predict what happens in the future also, because everything in the future is already predetermined. So looking at the current state sensor information and what has happened in the past, you can actually predict whether the grasp would be successful or not, right? Because like I said, the actions that it takes in the future are all predetermined. So we are looking in this work, we looked at whether that is possible. So looking at the sensor state, can we predict whether things can go wrong in the future? So we use like again a recurrent neural networks, specifically an LSTM, to do this prediction. So the framing in this learning is not that easy because there's a problem of labeling whether something is success or failure, and also knowing exactly when exactly when something has gone wrong is not easy. So at the moment, what we do is a nice way around it. So we purely label each trials as success or failure only in the end, but we still formulate it as a regression problem and try to force the network to predict as early as possible whether something is going to be a failure or success. And it sometimes can do it very, very, very well, and it can also do it much before something fails. So I'll give some examples of videos of it doing that. So on the left side, you see the predictions on the top. So if it goes high, it means it's predicting failure. And if it's low, it means it's success. So I don't know if you have the time to see, but maybe in the next example, you'll be able to see. But it can predict based on initial interactions whether something can be a failure or not pretty early, even before it looks like a failure. And that's very useful because it means that you have the scope of correcting for the failure in the future. And it's also a very nice learning problem and interesting that you can do this. It's not, I wouldn't say it's perfect, but it's got very good accuracy in predicting failure. There might be like false positives, but I think in terms of predictions, it was good. And I'll talk about recovery later. And all this learning is done using this 100 trials on that single object that I showed you before. It turns out it's also very transferable. So this learned model, which can predict whether something is going to fail or not, is also transferable to different objects. surprising. We are not very sure why that it is. Just that we observe this. It's sort of like same objects of similar shape but different sizes, but also of different shapes and sizes. And because also it's like a regression problem, you all by looking at the curves of these predictions, you can also infer some information about what is happening. We haven't really looked into what those information is, but yeah, it's something like we'll probably do in the future. Let's also point out that the coloring of the graph is dependent. So we use another heuristics to decide when something has gone wrong. So that's based on some simple thresholding. So the color that you see, which when the blue line turns to red or green, it means that we have predicted it to be a failure. It's not necessary that it becomes a failure in the end, but at least based on our heuristics, we have decided that's going to be a failure. And we do that because we are trying to correct that, and which I'll come to in the latest slides. Sometimes those heuristics might not be correct, but I think over time it tends to be very good at its prediction. So I think there are a few more examples of it doing well. Sometimes you can also see that sometimes it also tends to go to failure towards the end. It's still incredible given the fact that it's not been trained on any of this, and it's just been like it uses like 200 examples just to learn this non-trivial problem. Okay, like I said, once you can predict whether things go wrong in the future, you can use that information to correct for it. And because we are doing this open loop trajectory and we can predict much beforehand when the things go wrong, these corrections can be very simple, and you don't need to be like high bandwidth. So you can do a simple correction once, and that tends to actually correct for the mistakes. So again, here we don't have a really scientific way of doing correction, so it's based on some certain heuristics. So we figure out that certain types of actions helps the correct for the failures, and typically the failures are through like spinning of the object or slipping, and it seems like doing a motion in certain direction helps to correct for this. So if you can predict early that something's going to go wrong, then doing this simple action tends to correct for it. And that's how we did this study for now. But I think it's straightforward how to automate that part also of correction. But again, important thing is most of the time it's open loop. It does this correction only when things go wrong, and it does it once. So this is an example of where it's successful. And so you don't really need any correction, and there is no adaptation. And there is an example where it predicts failure and it's a failure, but and there's no adaptation at the moment. So it detects it's a failure and it turns out to be a failure. And in the next example, you'll see the same system doing exact similar graph motion, having a similar failure prediction. But in this case, we do a recovery before it actually fails, which helps it avoid failure. So you can see the predictions are almost similar. We made the decision that it's a failure, but it corrects for it quickly. So it's a very small correction. You don't see it, but you can also see this the slow motion video where it kind of shows. So that's the point where you decide that it's a failure and we need to take an action, and we do this very small corrective action, which we empirically found out helps recovery. All right, so that was I think the end of what I more or less wanted to show. In summary, I think there's some side notes that I would like to emphasize on, which is interesting, which I personally find very interesting and sometimes non-intuitive. Some of them are, soft robots can be really fast if you really want it to be. And the example is the first pi-stable gripper that I showed. It can detect an object and close within 2 milliseconds. So that is quite fast for what you usually associate soft robots with. And that is mostly possible because of the design. So it has to be purely mechanical loop. If you bring sensors and actuation, you're definitely going to slow down this loop significantly. So they can be fast based on how you essentially design the controller. They can be highly repeatable and robust. Again, this is something that is not intuitive. If you work in the static regime, you will find that there are a lot of uncertainties. You will never reach the same position again. But as long as once you're in the dynamic regime where you are working with static friction, things are very consistent. So you can actually get highly repeatable motions, even more than you think you might find with rigid robots. And they can be very fast and also very robust. And something that I didn't really cover, but they're actually very easy to learn. So in a lot of these, learning the dynamics of soft robots is much easier than rigid robots. So one of the reasons for that is the dynamics itself is not chaotic. It's always very well behaved. Whereas in rigid robots, if you have very less stiffness, you tend to be chaotic. There are also other reasons. So damping helps a lot, making it much more stable. And the fact that it's repeatable, it's again very important for the reason why it is very easy to learn. So these are some things that I find is sometimes not very intuitive, but something that's very interesting to me personally. And to conclude, I think if there's anything to take away from this talk, it's that there is a trade-off between open loop and closed loop control in software. So, and that is the actual trade-off. So if you want your software to be intelligent, not just think about how you design it, but also think about how you develop open loop controls if you can. Closed loop controls tend to be not good for them. Thank you. That's it from me. If any of you are interested, or if you know anyone who's interested in pursuing a PhD at UCL, I have a few openings. There's a link for that there. And that's it. Thank you.